Hey, we've made it to our final chapter in Chem 1. This is chapter 11, which is basically all about something that we're going to call colligative properties, really, in the end of it. That's what the main point that we're going to try to get out of this is. Okay, so first off, we're going to talk about the dissolution process, and really, we're just going to talk about some things that we have done in the past. Right, and what we're doing here is we're going to be looking at different solutions, and solutions meaning that when we've got multiple things mixed together, and we've talked about this before, where we have, right, a solvent that is doing the dissolving, we have a solute, those are the things that are being dissolved, and then the overall solution there. Right, and I've got some examples of different solutions here, whether they be, aqueous like our morning coffee, whether they be liquid like gasoline there, or whether they be gases like the air that we're breathing in. All right, those are all different types of solutions. Okay, so what we're going to do is just kind of do a recap, reminding ourselves some of the different ways that we can calculate the concentrations of solutions, as those are going to be helpful for us later on in this chapter. And so we're going to talk about the molarity, remembering that, right, that was the moles of whatever our solute is divided by the liters of solution, right? We've done that many times throughout this semester. We learned about a mole fraction, and we even brought that back up whenever we were talking about partial pressures a couple of chapters ago when we were doing our gas laws in chapter 9. And the mole fraction, remember, was that chi is equal to the number of moles divided by the total number of moles that are present in our solution. And lastly, we have their molality. I guess not lastly, because I got mass percent on there too, but molality was the number of moles of solute per kilogram of solvent, right? And so, right, all of those can be ways that we can describe the concentration of something. There's also a mass percent in there as the mass of whatever our solute is divided by the mass of solution times 100%. The first three are the ones that we're really going to be interested in going forward in the rest of this chapter, though. So molarity, molality, and mole fraction. Okay, so why don't we do a sample problem here where I've got a bottle of phosphoric acid. It says that it's labeled as 85% phosphoric acid by mass. We're given a density. We're going to calculate the three things that are like what we're going to use a little bit later on in this chapter here. So molarity, molality, and mole fraction. Okay, so from the density, right, I've got that density 1.689 grams per cubic centimeter. Okay, so why don't we assume, right, because it doesn't give us anything here, so why don't we assume that our bottle has, okay, we could find out that this really doesn't matter what we assume, because we could pour out any amount and concentrations don't change, right? If you had some 3 molar hydrochloric acid in the lab in a bottle, and you poured that into a little beaker and you walk it over to your lab station, it's still 3 molar hydrochloric acid, right? So it doesn't matter how much there is. So we can assume any amount here. I'm going to assume that there's 1 liter of solution. And if we assume that there is 1 liter of solution, that is really a 1,000 milliliters, which is 1,000 cubic centimeters. Okay, so this equals, right, 1,689 grams of solution. All right, so next off, right, I'm going to say, all right, what is the then All right, and then what is the mass of our H3PO4? So right now I'm just getting a bunch of pieces of information that I'll probably need going forward for the rest of this problem. So what's the mass of our H3PO4? Okay, well that is the mass of our solution times the percent as a fraction times that 0.85. So that is 1689 grams times 0.85. And so that is 1,463 grams of H3PO4. All right, what else can we find? Well, we could also find from that what is the mass of water. Okay, that is the mass of the entire solution minus the mass of the H3PO4. So our solution was 1689 minus the 1463, and we get 253 grams of water. Okay, so we got a bunch of information here, so let's see if we've got enough to kind of work out the rest of the problem here. All right, so let's start with molarity. All right, so the molarity for our H3PO4. All right, so remember that is the moles of our H3PO4 divided by the liters of solution. Okay, well, we assumed we had 1 liter of solution, so that we've got already. So what is the moles of H3PO4? Okay, well, that is, we have 1,463 grams of H3PO4. All right, times, all right, so 1 mole of it, all right, and so H3PO4 has a molar mass of 97.99 grams per mole, and so that is 14.7 moles divided by 1 liter, so it's 14.7 molar. All right, so that's our molarity there. All right, next off, let's calculate the molality of our H3PO4. All right, and so molality, remember, is the moles of the H3PO4 divided by the kilograms of the solvent, right? Not the solution, right? But the kilograms of the solvent. All right, we just found the moles of H3PO4, 14.7 moles. All right, kilograms of the solvent. Well, we just found up there earlier, the solvent in this case is the water. All right, and so we had 253 grams of water, right? Because it's the only other species that's present besides the H3PO4. So it's got to be the one that we're calling our solvent in this case. And so we had 253 grams of it, which is also 0.253 kilograms. And so I get this to be 57.9 moles per kilogram, which is another way of saying that this is 57.9 mole as a solution. Okay, finally, we want the mole fraction of our H3PO4. So that is the number of moles of the H3PO4 divided by the total number of moles All right, and the total number of moles is the number of moles of H3PO4 plus the number of moles of our water. Okay, so I've got the number of moles of H3PO4, but I don't have the number of moles of water quite yet. Okay, but I do have that we have 253 grams of water, and we can use the molar mass again, which is 18.02. All right, and so I can find that we have 14.0 moles of water. All right, so our mole fraction then is 14.7. That's our moles of the H3PO4. And our total number of moles is the H3PO4, that's 14.7 plus 14.0. And we get then the mole fraction to be 0.511. All right, so we went through all of those because, again, we're going to need those a little bit later on when we do our colligative properties. Okay, next off, we're going to talk about solubility. All right, and so some principles of solubility. And how much do things like to dissolve? All right, so the solubility of something, a lot of these are going to be things that you just already know, even if you don't know that you know. All right, so number one is, right, like dissolves like. All right, now again, you might not think about the fact that you know this, but you do. All right, because right, polar dissolves other polar things, and nonpolar dissolves other nonpolar things. And the opposite isn't true, right? When you have things that aren't alike, water and oil, they don't mix. See, I told you, you knew that, right? Those don't mix. But when things are similar, they do mix really well, and they do dissolve really well, right? So if you've got things that don't dissolve, like oil and water, so like say that you've got some vinaigrette in the fridge and you want to put that on a salad, right, and you get it out of the fridge, it's separated, right? It's got the oil on top and the vinegar on the bottom, and you got to shake it up before you put it on your salad. All right, well, if you've got things that are similar, okay, things that are polar, okay, so water is polar. Another thing that's polar is alcohol. Alcohol is polar. So if you've got a bottle of vodka, okay, and you were to, if you're of age and you can do that, okay, if you were going to take and pour a shot of vodka, you don't have to grab the bottle and shake it. No, because it's really well dissolved already. So like dissolves like. All right, so another way of saying that, right, is nonpolar substances have a poor affinity for water. So, right, again, right, if you were to ever go out on a boat or something like that and, you know, you're driving around, you might see like a little stream of like some gasoline sitting on top of the water there. It's because they don't mix very well there, right? But polar substances do dissolve easily in other polar substances like water, right, alcohols. And then another thing in there is that solubility of things decrease as the molar mass increases. All right, so it just means that bigger things tend to not dissolve as well as little tiny things do. And again, that kind of should make sense even if you don't really know it off the top of your head. All right, next up is some solubility stuff. How about temperature? Okay, it says at the top there, an increase in temperature shifts the equilibrium to favor an endothermic process. All right, now, even if we've kind of forgotten a little bit about this, but just remember that we've described these things before, right? That endothermic, right, is where we have a positive delta H, right? And that is where energy has to be enters a system. All right, so what we find then is that if you have a solid and you dissolve it in a liquid, right, that is usually an endothermic process. Right, and so if you think about that, right, what I mean by this here, right, is that, let's do it with this one. Right, it says that solubility tends to increase with temperature for most solids. All right, so again, I bet you've probably done something like this before, but like if you took some salt or some sugar and you put it into water and you tried to dissolve it, so you can put it in the water and you might stir it up, right? But I bet you really also know that if you were to put it on the stove, and you could try this at home, if you were to put it on the stove and start heating the water up, you can dissolve more of that sugar or salt in the water by heating the water up, right? That's because you are putting energy into the water, heating the water up, and that then is an endothermic process where we're going to dissolve more of the solid. All right, for gases, right? Dissolving a gas in a liquid is an exothermic process. So as you heat it up, right, you're going to have less gas dissolved. All right, so again, you probably kind of have a good idea of this as well, right? If you've ever had like a soda, if you've got like a hot soda, right? If I take my soda and I heat it up, right, it's going to end up, it's going to taste flat really fast. That's because of the carbon dioxide that is dissolved in the soda, right, has gone out of the solution and it tastes flat, right? No, you know that carbon dioxide really doesn't do anything in a soda like that. What it really does is that it inhibits some of your taste buds in there, and so it blocks some of the taste that you're getting. Whenever you do that, whenever you get rid of that carbon dioxide, it tastes flat, but what you're actually doing is you're actually tasting the whole thing. It's kind of a weird idea there. But all right, so solubility of gases decreases with temperature. All right, what about pressure? This again, I bet you money is that you kind of know this, even though you don't. All right, so pressure has a big effect on the solubility of a gas in a liquid, but it really doesn't have much of an effect on like solids or anything like that in there. So we're not going to really worry about that. But gases in a liquid, it has a big effect on that. And again, I bet you have done this. So if you have a can of soda or something like that, right? Whenever you get your can of soda, right, initially it's under pressure, right? In that can, there's a lot of pressure in there, and the gas is dissolved. And then you pop the top on it, and you open it up, and you hear that ch, right? Well, that's a bunch of gas that's escaping because the pressure in there, right? It was at high pressure. Now it's at atmospheric pressure, which is at a lower pressure. You've lowered the pressure, and the gas escapes. So the lower the pressure, right, as the pressure goes down on something, right, then the solubility also goes down of that gas. Right, and we can calculate this by doing an equation that we call Henry's law, which is the concentration of the gas is equal to some constant. All right, and that constant is very specific upon the gas and liquid solution that you're making. So it's not like a constant that is like, the gas law constant where you can use it for everything. You got to look one up that would be very specific for it. So it'd probably have to be given to you. All right, and then this is just the pressure of the gas. All right, so let's do a sample problem where we've got a carbonated beverage. It is saturated water with carbon dioxide at 0 degrees Celsius and a pressure of 3 atmospheres. So that's 3 times the normal atmospheric pressure. All right, we open our bottle at room temperature. Okay, so we've changed the pressure and we've changed the temperature of it. And it's going to come to equilibrium with the air in the room. All right, and so the room has some carbon dioxide in it, which has a partial pressure of carbon dioxide of 3.4 times 10 to the minus 4th atmosphere. We have a Henry's law constant for this, all right, which is 0.0769 molar per atmosphere, molarity per atmosphere, and 0.0313 molarity per atmosphere at 25. All right, what is the concentration of the carbon dioxide in the bottle before it's open? So this looks like it's going to be a really hard problem because there's all these different pieces of information, but is really going to be straightforward because we're only going to do a little bit with it. Okay, so if we want the concentration of carbon dioxide, that's the concentration of our carbon dioxide is equal to our Henry's law concentration times the pressure of our gas. Okay, so we have the concentration of carbon dioxide is equal to, all right, we've got, let's do for before it's opened. So before it's opened, right, it was at 0 degrees Celsius and 3 atmospheres. All right, and it said that we had at the 0 degrees Celsius one, we have a Henry's law constant of 0.0769 molarity over atmospheres. All right, and it was 3 atmospheres. Seriously, this is all we're having to do on this. It looked way more complicated than this, but this is really all we're doing. And so the concentration is 0.23 molar. All right, for part B. All right, I'm going to do part B. We're doing the exact same equation here. Yeah, I keep forgetting to put that second C in there. Okay, so, right, for this, after it's been opened, right, we have it at 25 degrees Celsius, so we have a new Henry's law constant of 0.0313 molarity per atmosphere, right, and we have a new pressure here, and the new pressure here is right up here of 3.4 times 10 to the minus 4th atmospheres. And so this equals 1.1 times 10 to the minus 5th molar. All right, so what this is telling us is, like if we look at it, right, before it was opened, right, there was a decent amount of it dissolved, 0.23 molarity, right? So that's its concentration. Once it was opened, right, notice that that concentration is much, much smaller. It's 1.1 times 10 to the minus 5th. And so, right, a lot of that gas has escaped out into the surroundings. All right, finally we're going to get to our colligative properties. Okay, now the definition of a colligative property is that these are things where the property of a solution differs than that of a pure solvent. Right, and there's a few of these that we're going to focus on. All right, so number one, let's see if this will let me advance. There we go. All right, so some of these are dependent upon the concentration, right, and not the nature of what these species are. So what that means is that it doesn't matter if it's, say, sugar, or if it's, you know, like, it doesn't matter if it's, you know, one type of sugar versus like another type of sugar here, right? So it's not their nature, right? It's the concentration. It's how much of them are dissolved, not what the specific species are there. Okay, and we've got these, they're called colligative properties, and we're going to have 4 of them. 2 of them are basically identical, so we're going to only do one calculation with them. All right, so we have vapor pressure lowering. Right, we're going to talk about each one of these specifically here in a minute. We have boiling point elevation and freezing point lowering. All right, these two are basically the same, so we're just going to treat them as one sort of a problem, and then you could work the other one by doing the exact same sort of stuff. And then finally, there's something that's called osmotic pressure that we're going to work with as well. Okay, so right, vapor pressure lowering. And so all of these are going to be dependent upon concentrations. And it could be molarity, it could be mole fraction, or it could be molality. And that's why we talked about those earlier in the chapter there. Okay, so first off, let's look at vapor pressure lowering. Okay, so the vapor pressure of a solvent over a solution, okay, is always lower than the vapor pressure of a pure solvent. All right, so what do I mean by that? Okay, is that remember that if you've got something like where we've got like a liquid here, right? It's going to have some sort of a vapor pressure because there's molecules of that liquid that are hopping up into the vapor phase. All right, and so what I'm saying then is that if you have a pure solution, it's going to have a very specific vapor pressure. But if you have a solution where you have mixed in something to it, right? So now it's sugar water or salt water or something like that, right? Then the vapor pressure is always going to be less than it once was. All right? And we can calculate that by saying that the pressure for the solution is equal to the mole fraction of the solvent times the pressure of the solvent. One other thing that we can do there is that the change in our pressure is equal to the mole fraction of our solute divided by the pressure of our solvent. There. Right, again, right, we're going to kind of run through these as well. So, right, it might be like, how much does the pressure decrease all right, if you have, let's say, 0.1 moles of sugar in, let's say, in 1 mole of water at 25 degrees Celsius. All right, I'm running this one on the fly here, so I'm going to look something up. All right, just to make sure that I get the right number here. So the vapor pressure of water is something that we can look up at 25 degrees Celsius. I was pretty close. I was going to put down 23, so it's 23.76 torr. That's 23.76 millimeters of mercury. All right, and so if I want to do this, right, what I could say is like, how much does the pressure decrease when we do this? So we could say that the change in pressure on this would be the mole fraction of our solute, which is the number of moles of, our solute. So that case, right, the number of moles of our solute, right, is the number of moles, I cannot spell, is the number of moles of our sugar divided by the number of moles total. All right, so that would be, we have 0.1 moles divided by our total, which is 0.1 plus 1. All right, so 0.1 divided by 1.1, and we're going to multiply that by the partial pressure of our solvent, which is 23.76 torr times 23.76. So our change in pressure would be 2.16 torr. And we know that it has to go down, right? So it would decrease by this amount. All right. Now again, I said we were going to, focus on our boiling point elevation and freezing point depression, basically like as like the same sorts of things, because as we see them, you'll see that they're basically the exact same equations as each other. All right. So what happens is that, right, if you have a solution and you heat it up, right, it does not boil until the temperature will exceed the boiling point of the pure solvent. All right, so what that means is that, right, water, say at atmospheric pressure, we know water boils at 100 degrees Celsius at atmospheric pressure, right, at 1 atmosphere. If you have sugar water or salt water or any water that has stuff that's dissolved in it, it's going to boil at a higher temperature, always a higher temperature. All right, and the difference we can solve for that is that the change in our boiling point is equal to the new boiling point, all right, minus the pure solvent boiling point. All right, that little knot symbol there is going to tell us that it's the pure solvent. A lot of times it tells us that it's an initial thing, but here it's going to tell us that it's the pure one. Okay, next off, right, look, they're kind of similar when we get to the equations here, but when we have a solution and we cool it down, it does not freeze until the temperature is below the freezing point. You've done this before too. All right, there's a reason why we put things like salt on snow and ice on sidewalks to melt the snow and ice. What we're doing there is we're turning that water into a solution, and when we turn that water into a solution, its freezing point is lowered, it goes down, and so we see that as it melting because it just is going to freeze at a much lower temperature, and so we can see that, and the change in that freezing point is equal to, now notice that the only real difference here is that these two things are opposite from each other, and it's just so that we can get the right sign on the change. All right, but this is the freezing point of the pure solvent. Right, so that's the temperature at which it freezes for the pure solvent. All right, now, these freezing points are also then colligative properties, and they are dependent upon the molality. Okay, so a little bit earlier there, right, we did the vapor pressure lowering. That was based on the mole fraction. Freezing points and boiling points are based on the molality of them. So we need to be able to calculate molalities in order to solve for them. And we can plug them into these equations here, where the change in our freezing point is equal to the molality times some sort of a constant. All right, and so that's a freezing point constant and a boiling point constant, Kf for the freezing, Kb for the boiling. Those, right, we have to look up in tables. They're different for whatever the solvent is. Okay, now I haven't brought this up yet because we really don't do a lot more with the vapor pressure lowering than we did. But I do want to point out that these equations are really best shown as the change in the freezing point is equal to I times m kf, and delta tf is equal to I m, oops, that's a b, kb, tb, and kb. All right, where I is equal to something that we call a Van't Hoff factor, but I is really How many particles are there in our solute? Okay, what do I mean by that? Okay, what I mean by that is if you have like a molecular compound, C6H12O6, when you dissolve that, it stays as C6H12O6. Right? Because it's going to stay the same. It's going to be that one molecule to one molecule. It's going to stay the same. But if you add NaCl, it's an ionic compound. Okay, when you dissolve NaCl in water, right, it is going to become Na and the chloride ions. And so we're going to get an I of 2. Okay, so I had to like break and take a phone call, so I'm picking back up. So this, like, if you have ionic compounds, right, it depends on like how many of those ions there are. Because remember, it depends on the concentration. So if they separate into separate ions, then the concentration is going to be higher than if you've got just a molecular compound where it's only going to dissolve one thing to one thing, right? So if you had, say, right, some magnesium chloride, right, well, it's going to break apart into a magnesium and 2 chloride ions, so the I is equal to 3. Okay, so the reason then that we use magnesium chloride, the reason we use magnesium chloride and we put that down to dissolve or to melt the ice and the snow is because it is going to change or lower that freezing point more than if we used, say, sodium chloride, and even more than if we use like sugar, right? Because they're going to have more ions that are dissolved, so we're increasing that concentration and decreasing that freezing point by even more. All right. So, lastly, I have osmotic pressure, and then we're going to do a freezing point problem and an osmotic problem, and even one more after that. So the osmotic pressure is given the symbol of a pi, and we're going to like this one because we have really seen this equation before, and it works out really similar to something else that's really not that difficult. Okay, well, osmotic pressure is the pressure that stops osmosis from occurring. Okay, and so what I mean by that is if I had 2 situations here, right, where I've got some water over here and say some salt water over there, and in between them is what we call a semi-permeable membrane, okay, which means that it has really, really tiny holes that allows for the flow of a few things through it, but it's not like, having giant holes that just allows like everything to come through like a sieve. Okay, so I've got my water there and I've got some salt water there, and what happens is that water likes to flow from the place of the highest solvent concentration to the lowest solvent concentration. So what I mean by that is that water will naturally just flow in this direction, all right? And as it flows through that membrane, there's going to be some sort of a pressure that's exerted, and that's called osmotic pressure. Okay, if you've ever heard of reverse osmosis, what that means is that we're going to push it in the reverse direction, and we could actually do that. And this is one way that we can clean up salt water and turn it into pure water, is we could take like a piston here, and we could push down on it, and if we push down on it with enough pressure, right, we could then reverse that pressure, and we could reverse osmosis and push it the other way. Right, so that flow of our solvent causes the pressure, and then if we apply a pressure that's greater than that pressure, right, then we get that reverse osmosis happening. Okay, so again, reverse osmosis can be used to prepare fresh water from seawater. All right, and this equation we're going to love. I bet you see this. This is basically PV equals nRT, but instead of it being like P for pressure, we're using pi for pressure. Everything else is the exact same. All right. Now, sometimes we will shorthand this thing, right? Because the number of moles divided by volume, remember, is molarity. So pi is equal to mRT, right? But it's the exact same equation. R is the exact same, 0.0821 liter atmospheres per mole Kelvin. Temperatures in kelvins, volumes in liters, N is number of moles. Right? It is the exact same thing as working a gas law problem. All right, now, right, again, we're bringing up that Van't Hoff factor here, which we talked about already. Right, but I do want to point out, right, hey, we did like sodium chloride. Here we've got calcium chloride as well. We did magnesium chloride as our example, right? But the Van't Hoff factor also comes into play when we're talking about osmotic pressure, right? That we can have a Van't Hoff factor that's in there. And it's not bad practice to go ahead and put it in, because worst case scenario, your Van't Hoff factor is 1, right? So molecular compounds I is 1. All right, ionic compounds, you have to break them apart and see what they turn into. All right, let's solve some problems, and then we're going to get out of here and be done with our final chapter of Chem 1. Okay, so our freezing point example. All right, so it says, what is the freezing point? So this, I'm not going to do a boiling point example, but it works almost the exact same way. All right, so what is the freezing point of maple syrup, which is 66% sucrose? And it gives us sucrose as C12H22O11. All right, so first off, we're going to calculate the molality. All right, because it's a freezing point problem, right? And remember, molality, right? It's not mass, it's molality. Okay, so we need the molality of this. So we are going to go with the moles of our solute. So again, it is 66% sucrose. Let's assume 100 grams total. I promise you could assume any amount and this will work. All right, I'm going to assume 100 grams. You could assume 1,000 grams. You could assume 1 gram. You could assume 3.3 grams. All right, I'm going to assume 100 grams because I can do the math in my head that then the moles of our solute, or the moles of our maple syrup, 66% of 100 is 66 grams. All right, I want to find the moles. So 1 mole, and the mass of our sucrose is 342.30 grams per mole. So that is 0.19 moles. All right, now, right, we want to find, because molality is moles of our solute divided by kilograms of our, right, solvent. So this is kilograms of our water in this case. Okay, so the kilograms of water. All right, so first off, the mass of our water is equal to the mass of our solution minus the mass of our sucrose So it's going to be 100 minus 66, which is 34 grams. And we can divide that by 1,000 to get that this is 0.34 kilograms. Okay, so now the molality is 0.19 moles per 0.034 kilograms. So that's 5.6 mole. All right, now let's substitute that into this equation, but this Kf isn't given to me. I should have put it in the problem, okay? But we would have to look up that Kf, and that is the Kf for the water. That's the Kf for the solvent. It would be given to you if you were to work a problem like this. It's 1.86 degrees Celsius per molality. All right, so our change in our freezing point is I, well, this is sugar, so our I is 1. Our M is 5.6 molality. Our Kf is 1.6, or 1.86, sorry, 1.86 degrees Celsius per molality is there. And this is 10 degrees Celsius. Okay, so the freezing point is, all right, it's Tf is equal to T naught F minus our change in our freezing point. Okay, so I took that equation from slide 13, right? If we were to go back and look at that, and I just rearranged it a little bit for us. All right, so the freezing point is, all right, the freezing point of pure water is 0 degrees Celsius minus this change in freezing point of 10. So the new freezing point of our water is negative 10 degrees Celsius. All right, let's do an osmotic pressure example here. A biochemist isolates a new protein and determines its molar mass by osmotic pressure. All right, so we've got a 50 milliliter solution prepared by dissolving 225 milligrams of the protein. We have an osmotic pressure. What is the molar mass of this? Okay, so let's remember, right, that our pressure is ImRT. All right, so a protein, the I is going to be 1. Proteins are molecular. Okay, so even if you don't know that, I'm going to give that to us right now. All right, I'm trying to find the molar mass, and I don't really know anything, but the molar mass is probably going to come from the number of moles somewhere in there. So let's see what else we've got. We have pressure, we have temperature. All right, so why don't I see what I can do if I rearrange this and I solve for the molarity. The molarity is equal to pi over IRT. Okay, so let's see if I can solve that. All right, so our pi, our pressure, is, oh, it's got 4.18 millimeters of mercury, right? And this is just like a gas law problem, so I need that in atmospheres. So I'm going to plug that in as 4.18 divided by 760. All right, that would give me that in atmospheres. I'm just going to plug it into this equation here. Right, I said that our I is 1, or R is our gas constant, 0.0821 liter atmospheres per mole Kelvin. I'm not writing all that out. And 25 degrees Celsius is 298 Kelvin. All right, so when I solve for this, I get the molarity of this is 2.25 times 10 to the minus 4th moles per liter. All right, now what else can I do? And so we have used, right, this piece of information, that piece of information. I got a couple other pieces of information up there in the problem, but what can I do? Oh, I bet you I could find the number of moles because I have the molarity 2.25 times 10 to the minus fourth moles per liter. And look up here, I have a volume, which is 0.05 liters. Look at that, I can get moles from that, so I've used another piece of information. All right, so we're getting through most of the pieces of information up there in the problem. And this equals 1.12 times 10 to the minus fifth moles. All right, I got moles, and I got one more piece of information up there in the problem. I have a mass of milligrams. Oh, that is 225 milligrams is going to be 0.225 grams. And remember that the molar mass is grams per mole. Right, looky there. I have grams, I have moles, boom. So 0.225 grams divided by 1.12 times 10 to the minus fifth moles. And this is going to be, I'm going to write down here, 2.00 times 10 to the fourth grams per mole. That's a really big number, right, when we talk about a molar mass, but proteins are really big structures, so that kind of does work. All right, last problem is another vapor pressure lowering problem. This one I've worked out already, so I'm not running on the fly here. Calculate the vapor pressure of water over the following ethylene glycol solutions. The vapor pressure of pure water is 19.83 millimeters of mercury. All right, so I've got the mole fraction of ethylene glycol of 0.288. All right, so I'm going to start here, and I'm going to say, okay, for A, I've got the mole fraction then of my water is 1, right? Because the total mole fractions have to equal 1. If you remember that from before, that was from our gas law chapter, right? It's just kind of like having percentages have to equal 100%. Mole fractions have to sum up to be 1. So it's 1 minus 0.288 is equal to 0.712. Okay, so the pressure, right? So the vapor pressure of water is going to be equal to the vapor pressure of our pure water times this mole fraction, 0.712, right, which then we get 14.1 millimeters of mercury. All right, so actually this should say, like, this is the vapor pressure for our solution. How about that? Because it was, right, the pressure of our solution was equal to the mole fraction of the solvent times the pressure of the solvent there. That's what I was working with. All right, on B, it says that the percent ethylene glycol by mass is 39%. All right, so again here, what I'm going to do is, number one, when I have a percentage, usually what I like to do is assume 100 grams, which then tells me that I have, right, 39 grams of ethylene glycol, which means that I would have 100 minus 39, which is 61.0 grams of water. All right, so again, let's get the mole fraction of our water, right? So that is the number of moles of our water divided by the total number of moles. Okay, so I've got 61 grams of water. I'm going to convert this into moles. So 1 mole over 18.02 is 3.39. And for our ethylene glycol, I have 39 grams of ethylene glycol. 1 mole of it weighs 62.07. So I get that to be 0.628. All right, so a mole fraction for water is going to be equal to, all right, 3.39 divided by 3.39 plus 0.628. And so the mole fraction is 0.843. Now we're going to plug it into the same equation up here on the top. So the pressure for our solution is that mole fraction, 0.843, times the, all right, the pressure of the pure water, 19.83 millimeters of mercury, and we get this to be 16.7 millimeters of mercury. And we've done it. We have survived Chapter 11. We have survived Chem 1. Good luck studying for the rest of your exams, and we'll see you soon.